Hello, everybody. Good to see everyone again. And I will say that the pen does seem to work today. It's the last day of our first week of doing these daily live streams every single day. I do see that we have a nice group of people that we have brought together. And I will say that I personally have had lots of fun trying to talk about these different topics based on whatever people are asking. Just as a welcome to all of the new people who are here today, I want to let people know that our goal here is to try to talk about problems or about areas of math that I can maybe tell some stories about that maybe can be understandable to as many people as possible. What does understandable mean? It just means that we don't want to talk too much about specialized mathematics that people might only learn in high school or later, like later high school and so on. There's a lot of interesting things that you can talk about where we can maybe explain the concepts even to people who are younger. And so when people ask questions, I'm always going to try to choose to answer the ones that maybe I think I can tell some kind of a neat story about that everyone can appreciate. As usual, I want to know what grade levels are represented here. Could people tell me what level of math you're learning in school right now? Every single time I ask this question, and we always get different answers. So I'm looking at this. We see a bunch of eighths, fifth, wow, sixth grade. So we got some young people here. I see algebra, 10th grade math, pre-algebra, algebra 1, algebra 2. So looking at all of this, I see that there's quite a lot of people who are doing math that's maybe around the age of middle school or early high school. So I want to make sure that whatever we choose happens to be a topic that as many people can understand as possible. Now, what should we talk about? As usual, this is a chance for people to ask questions. I personally prefer questions that maybe can cause me to tell you something that your teacher might not normally teach in school. This has nothing to do with your teacher being great or not great. It is just that you already have a teacher, and they're working really hard during this time, especially when many people are at home. And so the goal is to try to provide something that may be different. And what is maybe special about this particular live stream is that our topics kind of jump all over the place. So we're willing to talk about different topics. Now, that means that I will try to tell you some stories too, and hopefully those are interesting. So I already saw some things come out. Okay, so I saw that somebody wants to know about this thing called the golden ratio. I like the golden ratio because it's related to my birthday. Actually, my birthday happens to have the same digits as the golden ratio, but maybe we can get to that towards the end of this little lesson. First of all, what's this golden ratio about? Golden ratio is about the most beautiful rectangle in the world. So if I was to draw a rectangle, what might make a rectangle look beautiful? You know, that looks kind of beautiful. This one? Does this one look beautiful? Does this one look beautiful? Well, when you look at all of these, I'll say that this one's special. It's a square. So I'll say that that's a very special and very beautiful rectangle. In fact, we will call this a rectangle even though it's a square. Every square is a rectangle that just so happens to have the length equal to the width. This long skinny thing, I guess it's a rectangle. Is it nice? I don't know. Maybe not. Maybe yes. Depends on your personality. This thing here looks fairly nice. And what do I mean by it looks fairly nice? Well, you can have many different ways of deciding whether something looks nice. And actually, let me start first by not saying anything about golden ratio, but saying something about an even simpler ratio. And it has to do with paper. Does anyone know in the United States how big paper is? So in the United States, our paper, like normal paper, looks something like this. 8 by 11. Is that true? It's not quite 8 by 11. In fact, in America, our paper is 8.5 inches by 11 inches. I know that on this live stream, we also have people from elsewhere in the world, and you may not be so used to thinking about inches. Just as a comment for the people who are coming in from elsewhere in the world, here, I'll tell you what an inch is. The inch is where you take 12 of them, and 12 inches are 1 foot. I'm sorry, I guess I didn't really explain to people elsewhere in the world how big 1 foot is. Well, it's quite simple. It's just how long your foot is. Maybe not quite. Actually, I don't really know anybody in the world. I don't know anyone in the world whose foot is actually a foot long. So whoever they found back then to call that a foot, that was a huge person. Maybe they had some story. Maybe they pretended that the king had feet that were that long or something. Maybe it made them sound more impressive. For people in the rest of the world, 1 foot, I think, is around 30 centimeters. Maybe somebody in the chat can help to correct if I'm incorrect. But I think it's around 30 centimeters, and if that makes sense to you, hopefully that's better. But so an inch, that's an inch. And why 8.5 by 11? That's a pretty good question. I don't know either. But somehow all of America standardized on 8.5 by 11. And we said, that's our paper. And so whenever you are taking notes in America, it looks like that. Does anyone know what is used elsewhere in the world? In other parts of the world, the paper is a little bit longer and a little tiny bit skinnier. Looks sort of like this, and it even has a name. In the United States, the official name of the paper is called U.S. letter. That's what we call it. Is there anyone here from elsewhere in the world? Yes, you said it right. It's A4. So elsewhere in the world, they use A4 paper. Does anyone know how big A4 paper is? What by what? Yeah, I see that some people here are saying, what? To be honest, the first time I, in my life, ever learned that there was such a thing as A4 paper was when I went to a math competition in Europe. And I found out that all their paper was different. I always had thought before that all the paper in the world was that size. And suddenly we went to a different country, and it was that size. And then I asked, why are you so strange in this country to use paper like this? And they said, actually, you guys are strange in America. You guys use paper like this. Everyone else in the world does that. Okay? And some people have said, okay, maybe you're right. 21.0 times 29.7. Wow. 21.0 centimeters by 29.7 centimeters. Let's draw that one a little bit nicer. Now, who in the world would invent that? That seems ridiculous, okay? If you happen to grow up in America, you look at that and say, what were they thinking? Couldn't they at least have chosen some nice whole numbers? I mean, 21 is a whole number, but why that? Why not 30? Why not 30? 30 seems quite reasonable. How about 21 by 30? Does anyone know why the A4 paper is this way? This is actually pretty interesting. Oh, I see. Somebody is saying maybe it's because it was in inches. You know what? Now I'm curious. And this is where you guys have an advantage that I don't. You're in front of a computer with Google or with whatever you like to use. What is 21 centimeters in inches? Can someone tell me? Is it nice? I'm going to write approximately. And I'm going to hope that someone in the comments converts 21 centimeters to inches. The easiest way to do that is to type into your bar 21 cm in IN, and then you'll get some number. Do we have any luck there? 8.267. Let's call it 8.27 inches. Doesn't look very nice, but it definitely confirms what I had said, that this is narrower than that. Okay. And you see this 29.7, that's close to the 12 inches. So what we're seeing is that there was no good reason why they called the paper this size. In that case, does anyone know? I mean, inside this chat, does anyone know why these have this ratio? Aha! Someone said it's 1/16 of A0. And that's right. It's because A4 paper is like this. But have you ever looked at a magazine before? What's a magazine? I don't even know if people these days read magazines. When I grew up, we all used these paper magazines. You know what I mean? But nowadays, everyone has computers. But the deal is a magazine is like 2 pages, right? And so you could conceivably imagine that the way you print a magazine is that you print on paper like this, 2 of them, and in fact, on paper like that, you then, I guess, put a whole bunch of them together and staple. And this whole huge piece right here, this whole thing, giant paper, is called A3. Can anyone guess what A2 is? Especially if you aren't from another non-US country. If A4 is one of these, and A3 is 2 of these, so that you could conceivably print 2, can anyone guess what A2 might be? I see it's double, 2 of A3, that's right. So A2 looks like this. So the A2 is gigantic. A2 is now the entire thing I've drawn so far. I'm going to just draw a giant A2 there, so it looks like it's a giant A2. How about A1? Oh no, I'm going to run out of space. This is going to go over my head. So A1 will be that thing, and A0 will be, all the way down. So I'm just showing you that there's something about these papers, that they're designed in a way so that if you fold in half, or like the thing, if you take two of them together, you could fold it in half and it's interesting. You can use it as a booklet. But by the way, maybe some of you, if you're students, have you ever made your own mini magazine at school where what you do is you take one of these pieces of paper, I'm going to turn it sideways, normal US letter paper, oops. Has anyone ever done this before for a school project? Where you say, I'll take my paper, turn it sideways, do this, and then, you kind of just cut it down the middle and make a booklet. Have you done this? Yeah, you have. I have too. And whenever you do this, you get like a nice little book, right? And you can fold it and give it to hand in some homework. Did you ever notice, did anyone ever notice that if you look at these two sides, they're kind of narrow? I don't know if anyone else had this feeling, but when I was in school and I did this kind of stuff, whenever I made those books, it sort of felt like the sides weren't right. It sort of felt like each of those sides got too narrow when I did that. Yes, people agree with me. Now, how might I wish for my paper to be if I wanted it so that when I fold it in half, each of these is similar to what you were used to? You see, the magic about the A4 paper turns out that if you take A4 paper and you fold a normal A4 printer paper sheet you see in the printer, fold it in half, you get A5 size. But the A5 size, if you can imagine what happens if I fold that in half, somehow each of these two pieces has the same size, as the same ratio of length and width as what I had before. I see somebody already in all caps. Sophia Lin says square root 2. Okay, let's see why. So what you're saying is that suppose I want to make the kind of paper. This is the A4 paper. Actually, I'm already going to draw it where it's like in the booklet style that you want to use for your school project or something. Let's do it with white. So, it's like a booklet style. It's going to go across like this. And you want that somehow your paper is just right so that when you cut it down the middle, like this, you have the right ratio of the length and the width. How can I do that? I now am curious what ratio of length and width I should have. So I guess, let's call this W for width. Okay? So if that's the width, then I need to have the same ratio. So I guess I have also a length, and I don't know what the length is, but each of those cuts the length in half. So maybe I can say that this top is the length over 2, and that top is the length over 2. Now, can anyone help me write down some ratios? I need to know that the length and the width satisfy some kind of a consistent ratio. And so I need that the big one, like the ratio of the whole A4s, the whole paper's length to width, big sheets, length over width. Can anyone tell me what that is with variables? It is, somebody's asking, what's the question? The question is called, why do people outside the US use weird paper like this? And this weird paper has a certain ratio of length to width so that somehow when you fold it in half like a school project, then the pieces you get, the two halves, have the same ratio of length to width as what you started with. And so I see somebody typed L over W. It looks like a 1, but it's L over W. Because L is the whole big length, and W is this short length here. Next, I think what we're curious about is what is the half sheets? Length to width. Now we need to be careful. The length of the half sheet is W, because that's the longer part. When I say longer, when I say length, I always mean longer part. So it's going to be W divided by, now what do I divide by? I divide by the width of the short half. The width of the short half is L over 2. So it's L divided by 2. So that's 2W over L. Now I know that there's some kind of a relationship between these two ratios. They're supposed to be the same. And if they're supposed to be the same, I know that if they're the same, then L divided by W is equal to 2W divided by L. Help! How can I use this to figure out the relationship between L and W? What could I do? I have this equation, and I'd like to know what is this ratio from L to W. Yes, somebody said like L squared is 2W squared. Thank you, Ian Ray. I think what you're saying is I need to have this. Let's multiply both sides by L times W. Some people call this cross multiplying, but I can say I just have an equation and I multiply both sides by LW, both together. And if I do that, I get L squared equals 2W squared. In that case, how do I find the ratio of the length to the width? I need to know L divided by W. I guess I could divide by W squared. So if you divide by W squared, you get L squared divided by W squared equals 2. What is L squared divided by W squared? It is something squared. It is L divided by 2. And as somebody says, take the square root. So if I take the square root, I finally get that L divided by W is either the plus square root of 2 or the minus square root of 2. How many people think that the length divided by the width is negative root 2? No, it can't be. These are positive numbers. So it has to be positive root 2. And I'll get rid of this. Yes, I agree, Krypton BTW. It is not negative. So I find out that the ratio of length to width, if I want this magical property, then it should be root 2. Let's go back to our A4 paper. 29.7 divided by 21.0. Is there somebody here with a calculator? Because I don't have one on me. Can anyone tell me what 29.7 divided by 21.0 is? Please paste it into the chat. 21.0 equals 1.414 something. So in that case, this is close enough to the square root of 2. What I should say is that the ideal for the A4 paper would actually be to have a ratio of square root of 2. I just saw some people say that there's a lag. What I chose to do here is that earlier today, I taught my Carnegie Mellon University PhD level class, and we decided to use this ultra low latency for real. And it worked great. In fact, we were then able to have more interaction. It was much faster. So then I decided to just go ahead and do that also with this daily live stream. Because what that shows is that if you remember last time, we went with the normal latency and it also lagged. So I think what we're finding out is that basically at this time, there are a lot of people using the internet. Thank you very much for putting up with the streaming that we have. We are living in a world today when lots and lots of people are trying to use the internet at the same time. I can even tell you, in our state of Pennsylvania, we actually had just almost all of the businesses had shut down. And so this is a serious time. And I think I just heard that in California and in New York, now suddenly people have to stay at home all the time, I think. I'm not entirely sure. But it's unfortunate. So we'll do our best. Okay. So that's the A4, and that's the square root of 2. But that's not what people asked. People were actually curious. Oh, so people are saying in Maryland too. Wow. So people were actually curious about the golden ratio. So I'm going to take a sip of water, and I'll also talk a little bit about how you might see the golden ratio come up. For this, I'm going to start with, I guess, something that I learned when I was young, which was, if you have a sheet of paper, like a US standard sheet of paper. Sorry, I call it standard, but standard only in the US. And if you want to get a square, does anyone know what you use to get a square sheet of paper? The question that we're now moving to, thank you for asking, the question we're now asking is, what is the golden ratio? And to do that, I'm going to kind of move to talking about, something that's going to be very important to get the golden ratio. Fold it. Yes, exactly. If you ever want to get a square piece of paper, like to do origami or something, whether you're using American A4 paper or, American paper or A4 paper, what you should do is to grab this top corner and drag that top corner down to here to fold it so that you make a fold that looks something like this. That's going to go down here, and it looks like this and this. Have people done this before? You kind of fold the paper and you get a nice square, right? I'm not going to square the paper, actually. That's not what I was going to do. That would be very hard. If you're asking how to make a square that has the same area as this, that is actually quite hard. But here, we're going to just say that's how you would make a square. But this is making us think that, squares and rectangles might have something to do with each other. Did anyone ever notice when you did this that the strip you cut off is just like not very thick, in the sense that it's kind of a narrow strip? Did anyone notice this before? Like this extra piece that's cut off is kind of like skinny and long? Yes, this is how I always felt. I was like, yes, I want to make a square. It's so annoying. Why couldn't we just have used square paper in the first place? All I have to take off is this narrow strip. Well, now let me tell you about the golden ratio. The golden ratio is a different kind of paper. It would look something like this. And the golden ratio is the specific ratio of length to width. So that if you did this thing, so this thing is different from folding it in half like an A4 to make an A5 booklet. This is called, if you wanted to make origami paper out of your golden ratio paper, what would you do? You'd go and grab the top piece, you'd pull it down to around here, and it would cut it off. And there would be this fold in the middle. Okay? And then after you're done, you would just cut off your origami paper, and you'd say, now I can make my origami whatever. And what's left over is, something with the same ratio as what you started with. So again, A4 paper was the paper for which if you fold it in half, then each half is the same as what it was. This golden ratio paper is the ratio such that if you cut off an origami square, then what's left over is the same ratio as what you had before. And now let's figure out what that is. If I want to figure out what that is, I need to start labeling all of these things. So I have a W. That's the width of the original paper. I also have a length. I guess I can call that L. At this point, I'm going to say I'm getting lazy. What do I mean by getting lazy? The last thing we did with this A4 paper involved multiplying L's and W's, and we got some equation that had both L and W in it. But when you get lazy, what you say is, let me see what happens if one of those two numbers is just 1. And the reason is because if one of those numbers is 1, that will already tell you a ratio, because you can figure out what the other number is, and the ratio will be the other number divided by 1. And you don't have to worry about this W you're dragging around. So which one should we use? Let's make W equal to 1. So now W is 1. And we'll figure out what the length should be in order to make this cut off origami part, when you cut off the origami part, to make what's left over have the same ratio of length to width as what I had before. In that case, I need to start labeling more stuff. The original ratio for the original rectangle, we call it the golden rectangle. Length divided by width is equal to, well, that's easy. That's just the length is L and the width is 1, so it's just L. But now I need to know the smaller, actually I should say, this is not just the golden rectangle, it's the big golden rectangle. Okay, the big one happens to be that. And then the question becomes, what about the small one? What is the small rectangle ratio? Small rectangle ratio of the length to the width equals, what's the length now? The length is now 1, okay, it's 1, divided by, what's the width? The width of the small rectangle is just whatever is left over here. But what's that? How would you know? It's just something less than L. Is it 1? Is the width, is this little bit right here definitely 1? Doesn't look like it because it's shorter. I actually probably need to figure out what I subtract from the whole L. So the next question is, what's this blue length here? How much is this blue length here? I see somebody has already, Jiang Michael has already said L minus 1. A lot of people are seeing that this is L minus 1 because this particular length is 1 also. That's 1 also because we have a square here where it's 1 on this side and 1 up and down. And so I can take the whole L minus that 1 and I get L minus 1 over here. At that point, I have a ratio. 1 divided by L minus 1. Now those are supposed to be equal. So if I set those to be equal, I get L equals 1 over L minus 1. What should I do next? I guess I should multiply both sides by L minus 1 to go and try to see what L could be. If you multiply both sides by L minus 1, you get L squared minus L equals 1. That's because L times L minus 1 is an L squared and a minus L, which is there. Pulling everything to the same side, L squared minus L minus 1 equals to 0. And this thing is something which is a quadratic equation. And to solve this quadratic equation, if you have taken algebra before, then you actually can solve it pretty easily. If you haven't taken algebra before, it's quite hard to solve. If you're curious about how to solve quadratic equations, well, I have a couple of ways that you can use, whether in the course, the online course daily challenge, or whether in YouTube. You might see me even talk about this in a YouTube video. But I'll just say that from this point, you can in fact write down L equals, this is the quadratic formula I'm writing down at this point, negative b plus or minus the square root of b squared, which is 1, minus 4ac, which is minus 4 times negative 1, all right, all over 2a, which is equal to 1 plus or minus the root 5 over 2. So now I have two choices again. Which one is it? Is it 1 plus root 5 over 2, or is it 1 minus root 5 over 2, and why? Does anyone know why one of those answers cannot possibly be correct? Minus. Yes, people are saying that the answer is plus, and the reason it can't be minus is because of the fact that 1 minus the root of 5, the root of 5 is more than 2, because 2 squared is 4, and the square root of 4 is 2. The square root of 5 is more than the square root of 4, so even more than 2. So if it was 1 minus the root 5, you get a negative number. So it cannot be the negative. We get rid of the negative option. I wonder if I can erase precisely enough. Not quite. I'll put a plus sign here. It becomes 1 plus root 5 over 2. And if that's L, then the ratio of length to width, the ratio of length to the width is equal to just L divided by 1, which is 1 plus the square root of 5 over 2, and that happens to be about 1.618. And so that's the golden ratio. Golden ratio, basically you can tell a story where you're talking about folding paper, trying to cut off your origami paper, and see what's left. Why would this be considered beautiful? It turns out that this golden ratio appears all over in other areas of the world. I mean, all over the world, in honeycombs, in snail shells, and so on. And so it's because it just appears so many times, and related to the fact that you got this square cut off, that it's also very natural for people to look at. If you're curious why it might appear, why this property of somehow having a square cut off is so interesting and useful, I'll draw you a quick picture. I'm going to clear this part off, and clear this part off, clear this off, and I'll draw you a picture where I'll first start by drawing a quarter circle. Because, it was a square. So if it was a square, I could draw a quarter circle. But now, I'm going to do the same thing here. Because this has the same length to width ratio as what I started with, it actually means that what's inside here has the same kind of relationships as what I had before. So in that case, if I drew another quarter circle, which corresponds to another square over here, I could get that. You see, this thing that I just drew is like cutting off a square right here. Aha! But then I can do it again. If I do it again by cutting off the square, let me draw the square. If I cut off the square, I can do it again. And here I'll cut off another square. If you cut off the square, we can do another quarter circle. And I can do it over and over and over again. Let's cut off another square. What does this look like to you? Does anyone see what this looks like? Yes, it's a snail shell. And so this is showing how this particular golden ratio tends to appear all over the place in nature. There are lots and lots of neat reasons for this. So golden ratio is here. Hopefully you have a different understanding of all of this. And hopefully, even if you had seen golden ratio before, maybe you have a different understanding of paper. Okay, now let's see. What other questions should we get? I'm looking at all this and getting some paper at the same time. Oh, I see. I'm just looking at all of these. Again, I'm trying to find questions that are as approachable to people as possible. Oh, golden ratio and music notes. I think we can try to talk about that one. Let me see what I can do. And again, I'll tell you, I'm not an expert on this at all, but with the golden ratio and music notes, can I hit that one for you? I'm trying to think. Because, no, what I'm trying to think is like, how easy is that one to explain? So I think it would be a bit too hard to explain golden ratio and music notes. However, I can tell you something about music notes, and that something about music notes can be useful if you think about golden ratios. So it can be useful, and it can lead to the golden ratio, but it's the beginning of a very interesting conversation. So let's do that, because this is something that I didn't really think about until much later in my life too. And so I'm very happy to share with you things that I learned, and I think they're interesting. So the first thing to understand about sound is that sound is a wave. So that if you ever think of something vibrating, the vibration is what your ears hear. What do I mean? So for example, if I just start banging at some frequency, like this, your brain is thinking somebody is clapping at a frequency. I mean, frequency means how much time between, actually no, it means how many claps every second. But if you have a certain constant frequency, your brain says some magical stuff is happening. It sees a pattern. I would say that humans are really, really good at noticing patterns. That's what we love to look for. So one thing we could look for a pattern is that kind of thing. But has anyone ever noticed that, for example, if you have a fan, I mean like a fan which blows air in the summer, maybe if you don't turn the air conditioning on, has anyone noticed that when you start to spin the fan, at the beginning it starts to sound like top, 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 top. And then after a while, it starts to be like top, 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 right? Something like that. And then it gets higher and higher frequency. It starts to sound like it's going or something like this. The point is that there's actually, your ears are noticing a frequency that's going faster than what your eyes could notice or what you could otherwise sense. So sound is effectively noticing that something is happening frequently, very often. Now there's something else that we seem to notice, is that if you sing a note, again, I don't play the piano, but some people here might. If you play the note of C, there's a certain note in the middle of the piano keyboard, which is a certain C. Here's where I'm going to ask the chat. Do you guys know which one is like some C in the middle? Like, is it like C4 or C5? Do you know what I'm talking about? There's lots of C's on a piano, and like one of them kind of in the middle. Does anyone know what that is? I'm actually not a music expert. Okay, somebody said C4. I think I'll believe you. So there's a C4 music note, which is somewhere in the middle. Oh, people are saying it's middle C. Right. It's because somehow people will play bass notes. Well, for you guys, it's this way. Bass notes and treble notes and so on. And so, that's the middle C, C4. And it sounds like a certain something. But there's also a C5. C5 is the next octave up. We call it an octave. But it's the next, it kind of just sounds like the next place that the scale resets. But there's a relationship here. I said that somehow sound is talking about vibration. So when you have a C4, what's really happening is if you went and looked at what's going on with the air particles. I'll draw this way. If you look at what's happening with air particles, if you were just kind of eavesdropping, sitting in a part of your ear as the C4 sound wave goes by, you would notice that the air particles are vibrating in terms of like the compression of the air is causing it to vibrate. And vibration would mean it's doing something like this. It's going up and then down and then up and then down again and so on. This is a graph where this means time. And this thing up here means like how far something moves. There's a technical word for this called displacement, which is kind of like how far things are moving. So you could imagine if you had something that could wiggle back and forth as the C4 note went by and the time went on, it would kind of go like this. And then somebody said, yes, C4 is an octave below, but C5 is an octave above. The exact thing that happens with C5 is, if I were to graph the exact same thing, if they happened to both be playing at the same time, and both started at the same time, the C5 would finish one entire cycle in exactly how long the C4 finished one cycle. Oops, that looks ugly. I need to make this more to scale. It would finish in exactly half the time. And then it would do another one. Let's pretend this is drawn correctly. I just want to give you the idea. These should be identical waves, and that should be one wave, but somehow magically, this wave finishes exactly when that's only halfway. And your brain magically notices a pattern, and it says, oh, these two notes seem to sound nice if I play one and play the other at the exact same time. So when you are able to have two notes like this, then somehow the brain's like a nice pattern. It's just the same way that your brain is noticing patterns where, for example, sounds better than, there's like no pattern there whatsoever. Okay, so now what I want to talk about, the frequencies though. Frequency is measuring how many cycles are going per second. I noticed somebody said that A was something like 440 Hz. I don't know what C4 is in terms of Hz. Does anyone here know what C4 is in terms of Hertz? This is the fun part of having a live stream where people are able to respond in real time. I do know that the A that we often tune to is 440. But does anyone know what C4 is? I don't know. Okay, it doesn't quite matter. Your piano just blew up. Please be careful. Okay, then let's just make up some number. But, oh, unless someone knows. 262? You sure? Okay, if you think it's 262, we'll use 262. That's C4. That sounds like it could be. Maybe. Oh, you got it. 261.6. We'll use 262 just so that I don't have to write as much. We usually say that C4 is 262 Hz. What an Hz means? Hz means per second. Actually, sometimes you just write it as 1 over s. That is not 262 and a fifth. That's 1 over s. But I'll now write it in words and say per second. And so what's going on here is that this wave that's going across is actually making 262 blips like this every second. Now this C5, it's going twice as fast. So the C5 should be exactly double of that. C5 should be, it's going to be about, if I could multiply, 500 and help me, 20. It's probably going to end up being about 523, unfortunately, only because of the fact that I saw it was 261.6, and so when you round, it'll only go to 523. But this is actually supposed to be times 2. And the reason it was times 2, I'll just say, I did see a 261.6. That's how I knew this was going to happen. Okay? 261.6. Okay. But that's finishing in exactly, it's finishing twice as many every second. And so it's like a times 2. And in fact, we will often say that the frequency, this is a frequency, the frequency ratio of C5 over C4 is actually exactly 2. Okay? But I'm not going to write 2. I want to write 2 divided by 1. The reason is because I can do even more interesting things. Does anyone know two particular notes that sound really good if you play them at the same time? Let's just use C4 and something else. There's like a certain, they're like musicians, like if they play C, is it C that you play with something else? G, C and G, right? So what's G for? People with Google, if you can help me find out what G4 is. G4 is some other frequency. It's going to be a bit higher. The frequency getting higher means that the sound sounds like a little higher, and it means that it's making more of those every second. And can someone tell me what this G4, you're saying it's 392. Okay, I'll pretend that's right. 392 Hz. Now I'm going to do a calculation. I'm curious. Does anyone know what is the frequency ratio of G4 divided by C4? Well, we can use a calculator for that. Frequency ratio of G4 over C4. And the C4 one, you might want to use 261.6. It might be better. Ooh, we're getting 1.5 almost exactly. It's actually 3 over 2. Now, why might that be nice? Why might we care so much that it's 3 over 2? Well, what that means is that the G4, well, let's think about the C5, C4. The C5 finishes 2 cycles in the same amount of time that it takes C4 to do 1 cycle. Let's tell the same story here. The G4 finishes the G4 finishes 3 halves cycles in the time it takes the C4 to finish 1 cycle. Let me write that down. G4 finish 3/2 cycles in the time C4 finishes 1. I could say that, but this statement is exactly the same as multiplying both of those numbers by 2, because then it also means that G4 finishes 3 cycles in the time C4 finishes 2 cycles. And those are both small numbers. That's beautiful. When you have small numbers involved, that's how your brain can notice. Your brain is basically noticing that over there, something finished 2 cycles when the other finished 1 cycle. And here you're finishing 3 when the other finished 2. Your brain likes to notice these fractions that have small numerator and small denominator. That's actually what this has to do with music and fractions. So actually, whenever you're thinking about all those pairs of notes that sound good, the ones that sound the most similar are the ones that have the frequency ratio, which is the fraction with the smallest numerator and denominator you could get. Like if the numerator and denominator was 1/1, that would just be called the same note. Not interesting. 2/1 is the next simplest, and that's why you would call that an octave. 1/2 is just the opposite order, the same notes. The next simplest fraction you could make with small numerator and denominator is either 3/2 or 2/3. But both of those are just like flipping which 2 notes are you playing. Like the 3/2 is this way maybe, and the 2/3 is that way. And actually, as you keep looking at this, these particular fractions that come up, which are these simplest ratios, are how you can find out what sounds nice together. And it also turns out that those are somewhat related to what are called the Fibonacci numbers. If you look at all of these and you look at these fractions, as these fractions get bigger and bigger, I mean, another natural fraction is 3/5 or 5/3. And so these Fibonacci numbers tend to be related. And it turns out the golden ratio is deeply related to Fibonacci numbers. That's a much longer lesson. But that goes and shows, something. I wanted to show something that maybe is related to fractions, maybe to music, and to Fibonacci's, and to the golden ratio. What else can we take here? Let me take a sip of water. So I'm going to quickly answer a few things that popped up, mainly to say those are things that might be a bit too complicated. I saw somebody ask about logarithms. I'd rather not hit logarithms. One part is because I was using that on last week's weekly show. I saw some people asked about Vieta's formulas. Vieta's formula is very interesting, but that's actually part of the study of, say, quadratic equations or other polynomials, something that you would probably be able to learn in school as well. I also saw modular arithmetic. Here's what I'll say about modular arithmetic. It's a deep subject, which is really interesting. And for me, the first time I started thinking about it was even like looking at a clock, like as the hand ticks around a clock, and thinking like, what happens in 12 hours? And everything is going where you go what we call modulo 12. But again, that's a deep enough subject that requires, a whole class inside it, a whole course. In fact, we have an entire course on number theory, which focuses on that at the beginning. I saw somebody ask another question of why are there 180 degrees in a triangle? Well, this is kind of fun. I'll just share with you a fun and simple way to talk about the angles of a triangle, okay? So why are there 180 degrees in a triangle? This one has a very interesting answer. So the question was, here's a triangle. The angles, A, B, and C, why is it that A plus B plus C equals to 180? So geometry is one of these subjects for which you use the basic facts to go and deduce more facts. I'll give you a simple explanation of this. Actually, the first simple explanation is something that will look like it's just you could do it yourself. It involves tearing paper. Then I'll give you another explanation that uses some geometry. And then I'll do something else to contradict everything else that I've just said. So stay tuned. Okay, so the first thing is if I drew this triangle, here's all you do. You tear off this piece. And then you take that piece and you move it up there. So I'm going to tear off the B and I'm going to put it over here. And here's the torn off part of the B. I put it there. By the way, by doing this, I have set up something which has two lines. And I also have this line between them that looks too much like 90 degrees. I also have this line between them. And somehow, over here, I have the same angles. This you might see. This is something which is in geometry class. It's called alternate interior angles. If I have two alternate interior angles that are the same, then it turns out that you have the two lines which are parallel, like this. If you haven't taken geometry yet, it doesn't matter. I just hope it sort of feels natural to you. And that's all I want to get with this. And a lot of this you can understand in a way that just feels natural, okay? So I would manage to get somehow pulling this thing up there, I would get a parallel line, or at least part of a parallel line going in one of the directions, this direction, okay? But what else could I do? I could also do the same with the C. Let's tear off the C. If I tear off the C and move it over here, look. The important thing is because over here with the C, again I have these two lines, and I have this one line that's between them, and I have these two angles which are the same, and that will give me that this thing, this little bit sticking off, is also parallel to this. So that's telling me now that I've got one complete line which is all straight running across the top. Because somehow from this very top here, I should have not drawn it so high, I have to stretch. But from that top thing, whether you go in one direction or the other, the direction you're moving is parallel to the bottom. And so if that's the case, then if you go and add up A plus B plus C, what do you get? This is not rocket science. It's not like a sum of angles of a triangle. At this point, all I have is I just have one straight line, and it's cut into some pieces, A, B, and C. So now how do I know that those add up to 180? Can anyone say in the chat? I see the 180s, right? I have the 180s. And so since the answer is 180, because when you add it all up, this whole sum right here, let's use yellow, the whole sum here, this is the whole sum is equal to 1/2 of a full rotation. And a full rotation is 360 degrees. Why is a full rotation 360 degrees? Because some people decided that that's going to be the number we use for the full rotation. And it works well because it's easy to divide that into many other numbers. That could be a whole lesson in itself. And in fact, it is in some of the things that we teach. But here, I'll just say that's how it's defined. And so when you multiply it, you get 180 degrees. And that's it. Okay, so that's why the sum of the angles of a triangle is 180 degrees. That is true if you're on what we call on a flat surface. But I already see some people have asked, what about the angles of a triangle on a sphere? What does that mean? And that's in fact what I wanted to go to. So I'm glad someone asked this already. Let me show you what happens on the Earth. The Earth, by the way, is round. Anyone who thinks the Earth is flat, I have news for you. Okay, so this is the Earth. Let's pretend that's a nice round circle. And has anyone ever noticed that when you fly from one place to another place, if you look at the map that's on the airplane screen, it somehow seems like the plane is not going in a straight line? Has anyone else ever noticed that, you're sitting in the airplane, you look at I guess this is the screen of the map, and you're like, okay, I'm going from here, I'm going to there, and then somehow the plane does this. Has anyone ever noticed that? The first time I ever saw that, that really bothered me. It's like, why aren't you saving jet fuel? Why aren't you just going in a straight line? But the reason why is because it turns out that is the shortest path. Because if you go and look at a sphere, let me give an example. suppose you have two cities which are on the opposite side of the North Pole from each other. In fact, the two cities that I used to fly between the most, which are at the opposite side of the North Pole from each other, were, I always noticed that whenever I flew between these two cities, the airplane decided to go over the North Pole. You do something like this. Oops. It should be kind of roundish. So you do something like this. Oh, that's an eraser. That's even worse. Let's go back here. Okay. It would kind of go up and then down the other side. Okay, and it went over the North Pole. So, my stream crashed. Is that true? Are people okay? Yeah, okay. Again, I'll say that with the lag thing, unfortunately, we don't have too much control over that because it does turn out that a lot of people are using the internet these days. So I guess the most we can do is we can say, if we want to be able to have this interaction where we can talk to each other, unfortunately, YouTube is doing the best job it can. We have a few different options. If I choose the option which delays the stream by 30 seconds, well, that definitely will make it so that you won't get any lag. But it'll also make it that, you know, whenever you ask a question or I ask a question, we kind of have to wait forever to talk to each other. So that's why we're choosing this option. Hopefully the lag isn't too bad, but hopefully this thing makes it so that we can actually have a back and forth. So, okay. So now we're back here, and it seems like it wants to go over the top of the North Pole. That's right. And so if you were to draw that on a normal map like this, it would go up and over. I was in fact just in Australia. It turns out that if you're trying to go from Australia to the United States, this is what the map looks like. If you're going from the southern hemisphere to the northern hemisphere, if you're doing this, here's a fun question. Does anyone have a guess of what it looks like? I'll say, like, does anyone want to try to say what it looks like? Should it be like this? Up like this? Like the white thing? Should it be a straight line like the red thing? Should it be the curve on the bottom like the blue thing? Should it be something else? Does anyone know? It dips down, people think. The golden triangle, upside down. Upside down. What would that mean? How would you do that? Blue. Yeah, so you see, it's very interesting. It's none of them. Turns out, it does this. This is cool. This is really cool. So again, okay, yes, Australia is what upside down. So what do you mean? Well, I'll say it's very interesting. It's like it does both, and that does make sense because in some sense, what's going on is that until you get to the equator, you should be doing something that's dipping down, and as soon as you get to something that's going over the north of the equator, you bump up. And you can see that over here. It's like when you're north of the equator, it's more efficient to go between those 2 points where you sort of also use the fact that the circles are smaller up there. And when you're going from between 2 points which are both in the southern part of the hemisphere, southern hemisphere, it makes sense to kind of use the fact that if you go down a little bit, it's to your advantage because the circles, I'm talking about how wide the equator circles are, those are shorter down there. In the most extreme case, if you're very close to the South Pole, you obviously should just go through the South Pole, not kind of around it. So it looks kind of like that. But now people had asked about this, like, what about a neat? Yes, I agree. This is neat. This is really neat. I'm going to tell you something else that I thought was neat. In Australia, when we do daylight savings time, it turns out that they do daylight savings time in the opposite direction, which also makes sense because they're in the southern hemisphere. And so, because of that, if it used to be that the time difference between the US and Australia was like, I already forgot how many hours, like 8 hours. After the US flips daylight savings time and Australia flips daylight savings time, I kind of lost track. I think it becomes like 6 hours. It's just like because they go in opposite directions, which is very, very funny. So anyway, that's kind of cool. Okay, so now while we're talking about these different triangles on a sphere, I can actually draw some triangle on a sphere. Here's a triangle on a sphere. I'm going to take one point, which is at the North Pole. And you might ask, why did I draw that point there as opposed to really at the top of the circle? It's because this is a three-dimensional shape, and you should imagine that you're kind of looking down at the three-dimensional shape with a little angle, so it looks sort of like this. Right? That's your three-dimensional shape, so when you look at the North Pole, it should be kind of towards you a little bit. And then the other thing I'm going to draw is I'm going to take a point on the equator. And I'll take another point on the equator. So I have these 2 points on the equator, and I've got that 1 point up there. Now let's pretend that we're going to fly airplanes from each of those points to each other. What would it look like? Here's how you'd fly from the North Pole down. Here's how you'd fly along the equator. And here's how you'd fly from the equator to the North Pole. Now this is on the surface of a sphere. You might ask, what is an angle on the surface of a sphere? Well, on the surface of a sphere, if I want to know my angle, I just stand right here and I point one hand going, oh, you guys are opposite, point one hand going in one direction if I was going to fly the plane, and point the other hand in the other direction as if I was going to fly the plane. So what's the angle between these two lines? That one is 90. So the angle here is it's a right angle. This is a 90-degree angle. How about over here? What if you're standing over there? Well, if you're going to fly to the North Pole, you just go north. And if you wanted to fly to this direction, you would fly like straight at you. So I have like the angle between this and this. That's another 90. How about at the very North Pole? Well, because I chose these where one is right in front and one is on the side, then the angle there is also 90. This is what I call a right triangle. This is the most right triangle in the world. All 3 angles are 90 degrees. Yeah, this is quite funny. Like, it was the first time I saw this, I was like, what kind of triangle is this? But it is a triangle. And so what you find out is that somehow 90 plus 90 plus 90, is 270. So it does turn out that if you have a triangle on the surface of the Earth, sometimes the sum of the angles is not 180. Whereby sometimes I actually mean always. The only time that the sum of the angles of a triangle on the surface of the Earth looks like 180 is if you go to your backyard and you make a triangle on the ground where it is like a few centimeters by a few centimeters by a few centimeters. And if you look at that, since the ground looks flat to you, it turns out that that triangle has the sum of the angles almost exactly 180. But it turns out to be slightly more than 180 if you can measure carefully. And a very interesting topic is to find out a relationship between the sum of the angles of a triangle on a sphere and the area, how much of the sphere that it covers. That's actually the topic of a talk I often give to advanced high school students all around the world. But we won't have enough time for that today. So that, I think, brings us to I forgot to tell you the story. Oh no, there was going to be a story. Wish math was less abstract. Yeah, I'll say that I love how math is abstract in the sense that sometimes the real world gets kind of complicated. And so if you are able to find the abstract way to look at it, you can sometimes find the best way to analyze what you need to do. Story, did I promise you a story? Oh no, I think I might have forgotten the story. Oh no, thinking about the solution to the coronavirus. Oh yeah, the coronavirus question. I'll say that, yes, we are still actively working on this. I don't want to break the news of exactly what we're doing yet here in this session, because this is something that is actively being worked on. And whenever something is actively being worked on, it's important to make sure that team has the space. But maybe instead, I'll just use the last minute of this. I know you guys want to know. You'll be among the first to find out, I promise you, because I'm doing these daily live streams. So the moment that it goes public, I'm probably going to be very excited to tell you. But instead, I think what I'm going to do is I'm going to say a little bit about, this math being abstract. We're trying to use it for something. By now, I hope you're able to see that math, we can have fun with math and we can have fun talking like this. But ideally, if you go and learn how to do this math, if you go and learn how to think about these spherical triangles, that's what they're called, the more of this that you learn, what I will encourage you is, the more you should think about how you can use your skills to go and try to make some difference in the world. And I think that's actually, I'm just going to share a bit of philosophy. That's how I choose what to do. I mean, why am I doing this live stream right now? I guess I find it entertaining. That's one thing. But also, I thought, given that there are so many people in the world who maybe could benefit from this right now, especially right now when a lot of people are at home, I thought this is like the easiest thing that I can offer you that uses what I happen to know how to do to hopefully help as many people as possible. If I had a different skill set, I would be trying to think, how can I use that skill set to help as many people as possible? I hope that this makes maybe some influence on how you decide what you want to do. If you just make yourself happy, that's okay. But if you can find a way to make, 184 people happy based on who's watching now, that's a lot more fun. Related to how many people are watching, that was the end of this week's daily live stream show. If you liked what you saw, please do tell other people, and we'll be able to talk about all kinds of interesting topics of mathematics as we keep going through this difficult time. And until then, I wish all of you a very good weekend. Oh, as a reminder, I will in fact be doing a weekend live stream. That will be tomorrow evening, 8 o'clock p.m. United States Eastern Time. And that one we'll do a problem that I actually am giving. And then that Q&A will be not about specific math problems, but all kinds of other things, such as, how to study at home and whatnot. In any case, if you like any of these, please do tell other people. And until next time, I'll see you.